All right, thank you very much. Well, hello again. So, so we're going to have a panel. We have about, I guess, about 50 minutes for the panel, so we've got a good amount of time. So just a little bit of a comment on the format. I'm going to introduce the panelists. I have a couple of questions that we'll just ask them to talk about. But then after we're through with that, feel free to come up with audience questions and start asking. We can have ideally we'll have a spirited discussion about this, right? I'm sure you've all been holding your questions for the past hours, so so we can have a good discussion, right? So so just to remind you, my name is Vilas Sridharan from AMD, and we've got 4 panelists here from both MDCs, mega data center cloud service providers, and an OEM. And they have graciously allowed me to grill them with questions like they normally grill me with questions. So this should be fun. So just to introduce our panelists, we're going to start with Anil Agrawal from Meta. So Anil is currently working at Meta as a hardware systems engineer. His primary focus is RAS technology within the infrastructure, right? So he's one of the people that at the CSP at Meta is responsible for all that, the middle line infrastructure that we talked about in the previous talk, right? And so Neil has over 21 years of experience in the semiconductor industry, including a variety of roles, right? So now Drew Walton from Google he started Google's fault management team and is currently Google's fault management lead. He's previously led that work at HPE across ASICs, CPUs, operating systems, firmware, hardware teams, you name it, right? So he's done that, previously at HPE, and now within Google, he's developing a data-driven understanding of hardware failures in order to reduce failures and minimize their impact, as we've talked about. Rama, Rama, Bhimanadhuni from Microsoft. Rama is a principal software engineer lead working at Microsoft Cloud Hardware Infrastructure Engineering team, and he's developing firmware solutions to enable new cloud workloads, security, improve system availability, and hardware telemetry solutions. He's got over 17 years of experience, and he closely collaborates with all of key industry partners and stakeholders, including all their silicon vendors, right? And finally, we have Scott Ramsey from Dell. So Scott's a systems engineer at Dell Technologies working on PowerEdge server systems. He's spent over 24 years sustaining, designing, architecting, and diagnosing systems of various form factors from microservers all the way up to big iron 4-socket servers. Well, maybe not big iron, but 4-socket servers. So we've got a very distinguished panel here. And so, I'd like to really just kick it off and just, we've talked a lot, I think, about the key challenges, but I would like to just start by asking each of you individually just to maybe reiterate or expand on what are the key challenges related to hardware fault management that are faced by each of you in your existing infrastructures. And let's just start this side and walk down the line. So Drew, you want to start?
Sure. Mine's pretty quick. We need to figure out what to do when a failure occurs, and we need to determine whether or not the failure represents a risk of crashing the machine or causing a performance problem. And so understanding the hardware at a level necessary to make that decision is really difficult. And understanding how to analyze the data coming out of the machine to recognize those failures is difficult, especially as the variety of machines just increases dramatically with custom silicon and the accelerators we're building. So it's really a complexity, not just of scale, but of the types of things we're trying to understand and the depth at which we're trying to understand them.
Yeah, thanks. Rama?
Hello? Can you hear me? Can you? Yeah, I see problem like in 3 stages. First, when you introduce new products into the fleet, what do we basically to support the cloud workloads across compute, storage, HPC, or AI, you have a heterogeneous fleet, okay, which involves like multiple SKUs from different CPU, GPU vendors, the memory vendors. You combine all that, you can support that fleet, okay? When you bring up that fleet, right, how time to market is very critical, right? When you debug that systems, having the knowledge of errors and analyze them, understand, and address them during the development, that is critical. And if you look at the way we integrate this infrastructure into the cloud software services which integrates all these agents, they want to call similar APIs. Maybe the background of APIs can be specific to vendors. They don't want to deal with many. If you want to introduce a new SKU, it takes time. If you don't follow the standards, we see that gaps, we have to do the custom solutions. That is one thing I see. Second thing I see is once you put the SKUs into the fleet, how do we, like what Drew mentioned is, right? How do we manage that fleet? How do we identify which fruit exactly caused the problem, right? And how do we address the no issue found? Because if you don't know what problem is identified, what do you do? Like, you cannot keep the systems in repair state for long because it costs money, margins are getting impacted, right? You need to have that vendor analysis tools to identify and address the right fault through replaceable unit. Third thing I see is a customer experience, right? Like as you launch like the containers or VMs and which are running different workloads, like the workloads can expose the bugs in the silicon, process issues, how you manufacture them, right? And how do we bring the better customer experience using some availability techniques? Okay, that's all talks about RAS. I see like the fault management or the RAS we talk about is a critical challenge in heterogeneous like fleet to support different workloads in different stages of the node journey, hardware journey. Okay, the fault management plays key role. How do we standardize that so that we build standard services at a very software level to support all this? Those are the key three challenges I see in the node journey.
Thanks, Rama. Anil?
Thank you, Rama. So at Meta, we are slightly different, deal with different kind of challenges. And one of the key difference between, let's say, Google and Microsoft infrastructure is that all the consumer for our infrastructure is all inside. We don't have any kind of public cloud offering outside. So that gives us a degree of freedom and when we design a hardware fault management solution within our infrastructure, because we can own our own stack all the way to the kernel and above. Now, having said that, the challenges are still there because we have to deal with the hardware faults, even whether we get the error data through in-band or out-of-band. So we have a lot of challenges, and I have I looked into like top 5 challenges that we face today. Let me just kind of list that. Even we are kind of going through the odd series. Drew said only 1 challenge. Rama said 3 challenges. For Meta, we have 5 challenges. So the first one is silent error. Now, silent error issue is something has already been talked quite a bit now in the industry. And we have a separate, in fact, sub-project already started. So we are not going to talk about that here, but that's one of the top 5 challenges we face when it comes to the hardware faults and how do we deal with those. Second one is host not reachable. When we're talking about such a large fleet and monitoring and maintaining remotely, when host is not reachable, it's very hard for us to understand what's going on. And partly this is something created as a part of the fundamental architecture itself, where in our fleet, our single point of entry for every node is through the OCP NIC. And if something goes wrong, like a single point of failure, then host is not reachable, even though the actually host is working fine, but it's just not reachable. So how do we handle this challenge? We still are kind of digging into that. But that's a little bit outside the scope of the hardware fault management within the machine itself. So the last 3 issues are really a lot more near dear to us in this working group. Out of that, the third one is, how do we get the detailed error log information? Something we talked about already in the beginning. Detailed and complete error log information from each machine whenever there is any failure happens. There are existing standards. We get some data through the EDAC, through the BMC, but none of these solutions so far provides us the complete detailed information. And for every solution we put together, we have to work with the vendors. So very vendor-specific solution is what we're developing. And that doesn't scale very well for us. So we need to develop a standardized way of getting detailed error information for every event that happens, something we already start looking into. So unfortunately, this panel is happening after the presentation. So we already are developing this kind of requirements and defining the requirements for the solution what we are interested in. The next one is SMM, something Drew talked about quite a bit. And Vilas said a lot about the SMM. So SMM is really one of the big challenge for us. We are trying to minimize the dependency on SMM, but we cannot get rid of it right now, and we want to. So we need help from the community to develop a solution for all the error, or all the different error types, from all the components, and whether it's a correctable, uncorrectable, recoverable, or fatal, all the errors, we want to make sure that we get the data without help of SMM. Because SMM definitely provides different challenges for us, latency issues, because SMM takes the workload execution away from our software applications to the SMM handler, and so we have all kind of stall detectors logic, and we see the stalls all the time, and that's not acceptable. And the last one is, which is very near to me, is the error injection. Now, whenever we develop any solution, there should be a way to inject errors at scale to test out the whole end-to-end solution. And that is one area where I've seen industry is spending the least amount of time. So we need some help from the industry, right from the ground up, as we are developing new technology, new solutions. Think about how we can inject errors at scale in our fleet so that we can test end-to-end solution. So these are, I would say, 5 challenges we are facing today that we need some help from all the industry players to solve these difficult problems.
Right. Thanks, Anil. And Scott, I guess, can you list the 7 challenges that you face? Yeah.
So if it was 3, 5, do I get 8 or 10? Do I get to go?
I'm sorry, only 7.
Oh, shoot. Okay. Well, actually, I was thinking about how do I simplify it down. I want to, like, you guys hit the nail on the head. I mean, we have the similar challenges, SMM, all that stuff. But one thing I wanted to mention that might sound counterintuitive, what we talked about earlier, is that, today, the default answer is the log and to capture logs, and we capture a lot of logs. But when you get all these logs, you have all this data then to go and parse, and you have to go decode it. And so, as you think about new technologies coming online, I mean, no offense to the memory folks in the audience, but DRAM is, it's DRAM. There's not an active processor. We're going to have adapter cards with systems on a chip running. We already have systems on a chip. We've already seen that. So you have a system within a system within a system. You've got full system dumps, full system dumps, full system dumps, and you have to sort and go through all that. So, I think one of the bigger challenges is once we have the infrastructure, we get the infrastructure, it'll help have healthy conversations with silicon vendors about what's important to look at, what's the capture, what are your thresholds, what do we need to look at so that we don't have to spend, if the more data you collect, the longer it takes to collect, and that causes infrastructure dependencies, and then once you have the data, you have to spend a lot of time decoding it and figuring out what's in that. And I think that, that's one of the bigger challenges that we're going to see as we implement our designs.
All right, cool. Thank you all. So I'm going to ask one more question to the panelists, and then we'll open it up for audience questions, and feel free to ask questions about anything we've talked about here, any of the previous presentations, or just whatever you want to talk about, right? So I think the one other question that I'll ask to start is what are the additional challenges that you see coming in the next 3 to 5 to 7 years, right? We've talked a lot about the current challenges, and obviously we all agree that it's already a big challenge, a set of challenges. What else do you see coming? So let's just go down the line again.
Okay, you sure you want to go the other way first? Okay. So I think the things like CXL attached memory, basically, if Partha was here from Google, he would tell us Moore's law is ending. We're entering a golden era of opportunity because there are a lot of new things coming. And Every time I talk to someone about, well, how do you handle poison on CXL memory when that memory might be shared between multiple nodes? How do you know when to clear it? There are all these fault management topics that come up, and thankfully the CXL folks are on top of it and have been discussing this. But we've got GPUs, tensor processor units, and it's just, I think I'm reiterating what I said before, but I think that the challenge that I mentioned before, where the combinatorial complexity of the things facing us is just increasing, and with Moore's law slowing down, it's going to increase at an exponential rate, and we're just not prepared for how fast that's going to occur. So having some plan to deal with that exponential increase in complexity is really crucial to us.
Rama?
Yeah, I think Drew mentioned like we also have similar challenges. I think some of you might have seen the like other challenge we face is you might have seen the immersion cooling, right? And think about how do we do the fault management when you have immersion cooling, right? If you see like all the HPC and GPU kind of thing, they have a lot of power dissipation. It requires like next few years, many systems in the data center will have immersion cooling. And what does it make to fault management is you have like putting like few servers into chamber. When you want to service it, okay, you have to bring offline all those nodes, okay, if you don't attack this fault management challenges. To servicing, you need to replace a component like CPU, accelerator card, or memory, right? How do we address those kind of challenges? The like critical things is like if you want to, like in a normal scenario, like air-cooled systems and all, when there is a fault, you called out fault code or something, you try to identify the CPU memory problem or something. Maybe sometimes you try to replace one and you get second chance of replacing other component. When as immersion cooling, the cost associated for service is very high. Cost in the terms of money and also customer experience wise, because all that nodes in the chamber is trying to serve like multiple customers, right? You need to have like degraded system support that requires a software support, and we see one of that challenge. The other one is like the number of like systems within the server are increasing. Like as you mentioned, how do we collect the system crash terms from multiple systems, analyze those things, okay, and how do we address the availability of each one, right? If you're running a GPU workload, for example, you run some kind of workloads on thousands of GPU systems. If two of the systems failure, the workload has a performance like implications, and sometimes it may not run that much workload, right? There is a job interruptions will be disruptive. The cost of the customers will see the cost of that work, like their training model increases, right? How do we address that availability and fault management? Those are the key things I see.
Thanks, Rama. Anil?
So from what I've seen in Meta, one of the things that's going on, as you might have heard in the keynote also in the first day, is the AI infrastructure. So we are building a massive AI machine learning infrastructure, which is basically, you can imagine one supercomputer versus many, many supercomputers. Now, how is that infrastructure is going to be different from what we have today? Today, we have an infrastructure serving web applications, web traffic. A lot of resiliency is built into software itself. So therefore, when one single machine fails, our applications do not get that much interruption. And so the problem is how do we report the errors and do remediation and then repair the machines offline. But when it comes to the AI and machine learning infrastructure, even one machine fails in that cluster, the whole application goes down. So the blast radius is very high, very large. So all the different kind of RAS technology that was something developed by CPU vendors for the past several decades, which we really haven't used, as Drew was mentioning, that becomes so relevant now, or will be relevant in the AI machine learning infrastructure. So how do we make use of those features to reduce the blast radius, keep the machines running, even if there is a failure, so that the application doesn't crash? Is going to be very critical for us.
Thanks, Scott.
There we go. So I was thinking about how I want to pile on what I already said about we were already dealing with logs we talked about, but so I sort of answered my question already. But one of the things that's definitely going to happen is as technology changes and gets faster, everything is going to have some level of RAS, which means that everything's going to have some level of RAS management. Like we're going to have bit error rates are happening today. What's correctable? What's uncorrectable? And managing all those thresholds and making sure that, going back to our framework, that those are communicated to us, measured, and we sort of have the right infrastructure in place and update it for these changes to happen. I was thinking about just going back from our our embedded designs, and at first they were running off a NOR flash, which was rock solid forever, and then it's like, well, your code base grows, so now you have to go and get NAND. And guess what? Well, NAND needs RAS because NAND has certain faults that you have to just live with and manage. And so, we're going to be living with that and managing it. And that's also why we need lots of help in this work group because RAS isn't going away. It's actually going to propagate out. It's no longer just a technology for DRAM and DRAM management. It's for all interfaces.
All right, thanks. So I wanted to open it up for audience questions, comments, discussion. I can obviously ask more questions, but I think we'd all like to hear, from some of you who've been watching. So let's start over here.
Yeah, it's a really interesting topic that we need to solve the problem. One of the questions I have is how much we are willing to pay for it, right? For example, if you want to get the errors out of band, in band, then you need to duplicate some of the hardware logic to put the registers available on both sides, right? For example, also if you do a memory failure, like you can mirror it, it's going to cost you money, right? It's how much really we want to put a budget on it for a system for hardware fault management. Is there any kind of thinking on
Well, I can answer if it's okay with you all.
Yeah.
So I'm not prepared to give you a price. I don't do negotiations on prices, so go talk to someone else. But what I will tell you,
looking is not a dollar number, right?
right,
budgeting,
but that's kind of the tone of the question. But what I would say is that right now, if you count memory errors, your no fault found rate is on the order of at least 50%, and a large part of that 50% that was correctly recognized as a memory failure was a single bit error that you replaced. So, I think that it's pretty easy to say, I'm not replacing the wrong part anymore. My machines are staying up more often. That's worth a few millimeters of silicon. So I don't understand how that could be a hard trade-off to make. The savings are potentially very high here.
Maybe I'll just add on a small thing. Like, for example, a lot of CSPs, right, when they started the journey, nobody talked about RAS first, right? They want to first get the workloads, right? Then what they have seen is the margins. Once you bring the customers, right, and the standardization comes, margins becomes very critical. What happens is, if you have no issue found, you're putting the systems for repair state for months. Each system may cost think about GPU system, it costs few 100,000, 10,000. You look at a volume of million plus servers, right? That is the one cost. Second cost is customer experience, right? That, it will cost you more than the margins, right? Those two are critical. At the same time, there are small changes we have not done. That's what we are talking about, right? Bringing the accuracy, software changes, firmware changes, it's a developer time, right? That's what, okay? Where you want to do redundancy features, say you want to do full mirroring, those things, not many people are interested because, it again, is a utility companies. CSPs are utility companies, right? They have to work on it. You have to, that's how it.
But maybe if you make the feature easy enough to use and we have a use case where it's valuable, maybe it becomes worth it. So I guess what I turn around, put it back to you is give us some really compelling features and see what we're willing to pay.
Yeah, I think it's good.
Let me give you my perspective a little bit. So when I was at Intel, I used to get the same kind of question, and I didn't have the right answer, right? But every time I would position some RAS feature, okay, it's going to cost some money, right? So are you willing to pay for that? At Meta, my mindset completely changed 180 degrees. Now, the question that raises in my mind is how much savings I'm going to have when I deploy certain technology to help me or help the whole fleet efficiency. Because we spend a lot of money, a lot of time in repair, maintenance. You talk about the size of fleet, right? So this technology actually is going to help us, or helping us actually already, and will continue to help in saving a lot of money. So the right question probably would be how much money you are willing to save by using this technology, and the answer would be a lot.
On follow-up questions to that, but yeah, go ahead, Scott.
No, I was going to say. I mean, we actually, yeah, we look at our operational performance, if you will, and so that definitely helps. I think the other thing too, I was going to pile onto that was, some of the things we've talked about today don't just help in the case when a fault happens. Like we've talked a little bit about the monitoring and other things, and there's been other groups talking about telemetry, predictive failures and things. And I mean, there's a interesting transition where you can take a situation that is asynchronous and unbounded and maybe make it more of a predictive. And I like to use the analogy of like F1, like pit stops. Like you can do measurements and you can be proactive about things. And if you make an investment and make an investment in the infrastructure, it can make your business more predictable. And that tends to make a lot of executives happy. So,
so maybe a follow-on thought is it'll be good. Maybe there is a benchmark established so that people can measure how good it's performing, right? So people can say all the management can go and look at it and say like, yeah, I'm doing, I don't know, whatever the scale, right? Maybe.
Yeah, I think that's a very good point, and we are already defining some ways to measure, like annual crash rate or annual interruption rate that Microsoft has, and mean time to repair, to really start measuring it in our current fleet, and then look at whenever we are deploying a new feature, how those numbers are changing.
Thank you.
So in the previous presentation, you mentioned that the out-of-band monitoring would require hardware enablement from the silicon vendors. What's the rough timeline for that, or the rough intercept points for that hardware enablement?
Yeah, I don't think we're here to talk about specific silicon roadmaps, right? I'll let you guys answer without talking about specific silicon roadmaps.
we needed it last year.
We need it now. I mean, so both Vilas and Yogesh will tell you the pressure from us is pretty high.
I mean, like, I'm willing to join this coalition of the reluctantly willing. Like, what do I go tell my CPU manufacturers? Like, what's like the magic word to ask for to say, we want this and we want it yesterday?
OCP, fault management infrastructure.
Okay, all right, cool, thank you.
Yeah, thank you, and come join us. We'd love to work with you.
Yes, another question about the previous presentation. You talked much about machine check exceptions, pretty much. How does that pan out to different kinds of failures? Let's say a voltage regulator on a board or some external component that is also already being captured by the BMC. How would that work? And to add to that, how would we treat combinatorial problems where we have indications manifesting in multiple components, multiple parts of the system, and we want to combine them together? And if we think about the systems we're building today, they have so many different components that could even operate independently, and how do we treat that with this model?
Yeah, I can speak to that. That's a really good question. So if you remember the picture we had something called the hardware fault monitor. And so when we get error logs from a GPU or a chipset, that also goes to the voltage regulator's clock power thermal and gathers logs. And what you can do with CPR is chain the logs together. It's kind of like a table of contents at the beginning. And so you pile up all the logs in a bundle, send them to the analyzers, and then what happens is the analyzers recognize particular CPR GUIDs that they can handle. They handle it, and then the key to understanding which of, so then each analyzer, you're right, is independent, and they're not necessarily reconciled. And so the way to look at that is to classify errors, and I've used the classification primary, secondary, and tertiary. A primary error is like a memory controller saying, I've had an uncorrected memory error, or I've had a corrected memory error. You know where the problem is. A secondary error is something along the lines of a timeout, where you requested a transaction, you didn't get a response. In that case, you don't know where the problem is, but you know the general direction that didn't respond. I'm sorry?
This is part of the spec that you're working on.
Yes. I mean, these are definitions we've talked about in the group. And then tertiary would be like, I've gone sync flood or viral, where something really bad happened, but we don't know anything about where it is. So then what happens is each of the analyzers would tell us, you know, kind of the significance of the error. Is it primary? Is it secondary? And what I would generally say is that if you have a power error and a memory error, and the power domain was related to either the CPU or the memory, then it's probably a power problem. So ignore the memory problem. You may try to remember that it happened and see if it repeats, but usually the environmental things take precedence over the things the chipset registers, because the chipset can't operate correctly if it has crappy power.
I suggest that you add another two categories. Silent errors that are not manifesting in your primary detection in the first place, and errors during hardware stressing.
During what?
During hardware stressing or validation tools that you want to group them together.
And along those lines, we've talked about that. And one thing I would really like to encourage people to consider is giving us, I would like to have, in my dreams, I would like to have a redfish interface where someone can say, I'm doing this test or this workload. And then when we log errors, we can embed that into the bundle of error logs we send up. And what that would allow us to do is, okay, so we're testing memory. We have a memory stress test. I'm sorry, memory vendors. I'm not trying to pick on you. I see Paul glaring at me. So what we would do, though, is I'm saying I'm doing A's and 5s right now to memory. And then I do pseudo-random numbers. Now I'm doing row hammer. And if I knew which test was running and I knew which errors I collected, then I can correlate the errors with the test and I can tune my test time. There's usually a knee and a curve when you test something. You find a lot of things quickly, and then as time progresses, you find less. And so if we do the right thing with this infrastructure, we could even figure out how to find the knee of the curve and optimize our testing so that we find the most things as fast as possible. But this is me dreaming big. I think I'm going to be thrilled when we get the out-of-band hardware. I want to keep the pressure on the vendors. But we are thinking about just those things, and I've got ideas, and I'd love to hear your ideas. But I think that if we have a unified error logging infrastructure that we all sign up to use, that we can do things like that create new capabilities that we just couldn't have dreamed of before.
Thank you.
Oh, sorry, anyone else want to add to what Drew said? No? All right.
Yeah, so thank you very much, and this is very helpful, and I'm sure it's going to have a big impact. One question I had during the presentation, like the previous presentation, was like we are going OOB first, like out of band first. So that means currently, as with my very little experience, the BMCs are like either single-threaded or very lightweight processors, and I don't think they can handle this many workloads which you're pointing out here. So are we going to go back and influence the BMC manufacturers or hardware spec? Like we need more cores or more interfaces to do all this heavy lifting?
So I can speak to that. I came from I wish Steve Lyle from HP was still here, because I worked with him on a project. Oh, he is here. Okay. So you go talk to Steve. But this is something that HP Superdomes do today, and it is doable. And we've done it with lower powered processors than a typical BMC. The key is to understand a couple things. Queuing theory is important. The other thing to understand is that when you look at uncorrected errors, they don't happen that often, so you tend to get a huge chunk of data, but relatively infrequently. With corrected errors, you might say, well, I want to see every one of them. But you really don't need to see every one of them. You can use queuing theory and rate limiting to get a representative sample, and that is frequently all you need. And in fact, I'm less worried about understanding what's going on in the case where I'm getting a flood of memory errors, because it's obvious. You know, you're getting a flood. They're steady. You have no trouble seeing new data and understanding what's going on. The thing that scares me more is that our current chipsets tend to say, I'm going to get 10 errors, and then I'm going to tell you about the corrected error. And that 10 errors, or X errors, whatever it is, could take 10 months to gather. And what I want to see is the very first error, and then I want to say, shut up for a second or two, and then show me the next one. And so I'm more worried about seeing the first error and then getting a representative sample quickly of the errors as they start to occur, so that I can take the earliest possible action.
Just one small thing to add, like one is the BMC capabilities, and also the availability of the BMC also plays important role. Security of the BMC also plays important role, because like you're depending on those to forward even to the OS, right? There is some work to be done in that area, right? That's why like the implementations like harvest all the data, some critical information, some people may use like in-band also. It provides that infrastructure, all right? You get majority of like 95% of the problems. You are solving P0 problem, right? Yes. There are some corner cases like, but yeah.
I think one more challenge I see after in Meta is like the BMC is not a single BMC anymore. It's split across multiple GPUs and FRUs and things like that. So now we're adding one more layer of aggregation within the system before even pushing it outside for further analysis. But yeah, I agree. Yeah, thanks.
Yeah, and so that rate limiting and being thoughtful about what you're aggregating is critical.
And I guess maybe I'm just going to add to what you said, Drew, right? Like even today for, you know, in-band logging through the OS, even if you think you're seeing all the memory errors, you're not, right? I mean, you just aren't, right? Because the typical MCA bank or, you know, whatever error logging bank can log one error at a time. By the time the OS clears it, you could have had 100,000 or a million more, right? That happens all the time. So even the OS is just getting a sample of all the errors. The BMC is just getting a slightly different sample. Maybe, you know, it's not a like fundamental difference there, right? So.
So I hope I understood what I saw. But if I did, then I think that the emphasis right now is on a single node, a single source of error, you know, within one platform, basically. But I think that there's a lot of potential if you, especially when you have fleets of millions of servers of the same kind, to apply AI and machine learning. If you have enough telemetry, then you can identify issues before they even happen and identify a trend even within regions of the data center. I'd like to.
Yeah, we have a proof of concept where we've done that. Yes.
Okay.
I can't say much more than that, but you are absolutely right.
I can't also say much, but we are collaborating on that.
I think Microsoft even published some of the work.
So, Rama.
Yeah, so, yeah. There is some work published, and also like every CSP, because
We're doing
what we have asset, right, is the data, right? We have like millions of servers data we have. The reason we are asking for all the data to come and analyzer tools is how do we prevent the customer experience, right, hitting the hardware fault, right? Once you get, that is like a next priority is once you get the problem is not having the sufficient telemetry across the scale, yeah, is the problem.
Yeah. Okay. Thank you.
All right. Any other questions? Okay. So I think I'm going to ask one more question for each of you, and then we'll close the panel. So, you know, we've talked a lot about this, right? And I guess it'd be good to hear in your own words for each of you sort of what is the role for standardization? Like, why are we pursuing standardization, and where do we think OCP can help, right? Like, I mean, we've kind of touched on it, but I think it would just be good to kind of reiterate like the message here, right? Like, why are we doing it this way, right? So now I'm going to start the other direction. Yeah.
Oh, the OEM gets to go first. No, I mean, I think, sorry, this mic's a little different. You know, standardization is super important because, you know, like, just like you guys talked about, you wouldn't talk about maybe the findings you guys have of your models for your data analysis. That's where the value is, but you know, you need the plumbing to get there, right? And so it's sort of like, I think about it this way. I mean, we need to have the right widgets designed in the industry, and standardization happens, and it gets, you know, nobody wants to go and figure out when they fix their sink, what's the hose? I mean, that drives me crazy. I got to go to the hardware store. I got 100 different hoses. I got to find the right hose. Oh my gosh. I care more about, you know, what kind of fixtures do I have on the sink, right? And so the standardization enables us to just, you know, leverage and commoditize and make the stuff underneath the sink, makes it really easy, and it just gets done. And then we can innovate on top of that, and it's better for everybody, you know. And it's also better because in this case, because we're all using the same parts and the same vendors, and you know, that helps too, right? For communication of the vendors, they're coming to us, they're coming to Google, they're coming to Meta, they're going to all the different vendors, and they're having to say the same thing 8 different times. And if it's all standardized, you know, it just makes all the communication a lot easier and simpler. We're all saying the same thing, the same language, and makes sense.
Yeah, I can't add anything more to answer that question. Maybe I can just provide one perspective, that today, when we look at the error information, and let me just give one example of PCI errors. So in a system, when there is a PCI device, there is a receiver error is detected. That's the information we get at the fleet level. Now, the receiver error itself is not sufficient for us to figure out what to replace. Do we replace the end device, or do we replace the switch? Where the problem is. So the point is that in today's design and architecture and the specification and implementation, the error information is very limited. We need to add more information into the error domain that can help us automate the whole repair and remediation flows. Today, there's a lot of hand-holding. Let's try to replace this first. Let's just put this thing again, reseat it, and reboot the machine, and let's hope that machine recovers and gets fixed. The problem is fixed. It works fine for certain kind of failures, but it is not really scalable. So standardization and higher level of error information, the fine granular error information at scale is what something we are looking for.
Yeah, I want to add a little bit different perspective. Like, if you see the hardware ecosystem, right? You have like silicon vendors, right? You have like firmware or software system providers or like inbuilt software. Then you have OEMs or ODMs, right? Who like make the end product and right ship it. You see how standardization helps like all three. I think Vilas talked about, should he call like all 4 of us to support the CPU error, or should he give like same tool? Okay, it helps them ecosystem, right? It helps us because we are able to root cause the issues, right? That is one way. The second way standardization helps is like you see like OCP as a open system firmware, right? It has like a platform firmware, open BNC. Before, if I want to do any addition, right? Like either we develop our own and give it to the vendors to integrate that into, let's say if I'm buying a system from Wave, Quanta, or I develop end-to-end product, right? Now I'm able to do the value add on top of, because I have a source access, okay? I can implement like all the error reporting standardization, some improvements, right? It helps the firmware software changes where we can add value add, okay? The solutions. Third thing is how does it help OEM, right? It helps with warranties because like they don't need to, if you find the issue correctly, if you have right fault management, they don't need to pay for the warranties because you are only replacing the part which is needed. Otherwise, you will be replacing, okay, replace the motherboard, right? What I see is like standardization, not enforcing by like OCP. How does the each one gets benefited, participate, and each one has a benefit getting out of it.
They had really good summaries. The one thing I would add is that we've noticed failures that are workload dependent. So we have our workloads that we run on for our internal things, and then we have these cloud customers that come and load things on that are a little bit different than what we run, and we suddenly see different errors on the machines. And I imagine those workloads are running other places too. Wouldn't it be wonderful if through standardizing the error logging and the error analysis, that when that company first saw the problems, they worked with the silicon vendor to recognize what's going on and put the appropriate analysis rules in for that engine, and then the silicon vendors just give us all the rules. And so I learn from the workloads we're not running. And so when those workloads suddenly appear, we don't break. And so I agree with everything they were saying, but I want to pile on with that what we'll end up doing is helping each other have a more reliable fleet, and give our customers a more predictably good experience, while at the same time helping the vendors make their products better.
Yeah, thanks. So those were all really great points, right? And definitely, Drew, to your last point, right? It's, we presented a framework. That framework isn't static, right? There are going to be updates to each of the things, and as we learn, as silicon vendors learn from one, workload or one, we can drive that knowledge across the rest of the industry, right? I mean, this is fundamentally an area where we don't want to compete, really, right? Computing's got to be reliable, period, right? And that's what we try to enable, right? We don't want to be competing on this, right? So all right, I think we're going to close the panel. I wanted to thank everyone here, right? And just last word I'll say as the moderator, right? My view of this general effort, right, overall is, if you look at the industry, there's tons of RAS standards and this and that, right? But they're all designed for computers that look like this. Realistically, the cloud is the computer, right? And so we've got to redesign our RAS standards to reckon with that, right? I mean, that's kind of the thing that we're trying to do, right? Is reckon with the fact that there's these giant computers out there, and the solution space is different, right? And much more, and potentially much more efficient, right? So thank you, panelists. Thank you, audience, for appreciation.